Now we're going to take a look at a parallel circuit, which is a little bit different from the series circuits that we studied previously. Now, a parallel circuit is one in which the current can split up and each resistor has its own path, so it's not all stuck within that same road. Okay, so parallel circuits have one big advantage in that if a piece of the parallel circuit is removed, for example here, if we take out this R1, the current can still travel through the other two spots. So if we were to make, for instance, Christmas lights out of a parallel circuit, it would be great because if one burnt out, the rest of them could keep running. It doesn't one burning out, it has no effect on the other lights. Now, it does have an effect though when it burns out. We'll see that in a minute. In our houses, so circuits in houses and buildings, they are built in parallel, and that is why. So if you remember in series, when we started plugging in multiple light bulbs into the series circuit, they started getting dimmer and dimmer and dimmer. So that wouldn't be very good if you designed a house that when you had turned on more than one light, that the lights progressively got dimmer, so less voltage or less current was able to go to each individual light as you plugged in more and more. So houses are designed in parallel. So when you plug in a light, it has no effect on the other lights that are in the system. It creates its own circuit with the battery or with the electricity source. But parallel circuits, as we'll see in a second, there are some reasons why they're dangerous and reasons why, for instance, with a power bar, we can plug multiple things into a power bar, but they say never to plug a power bar into another power bar, and we'll see why that is. So on the right here is my circuit I have set up. So if we take the amp meter here and connect it in there, we've just created a circuit. Okay, we've created a circuit, like a simple circuit like we saw in the previous video, with just a battery and a light bulb. And I have an amp meter set up at each location to continuously measure the current in each branch. Okay, so we have a normal circuit running, so the electrons again go from the battery through the light bulb and back again. So the light bulb currently would be using the entire voltage, 9 volts of power, as the electrons travel through. Let's see what happens when we hook up a second light bulb. So see, nothing happened to the first light bulb. Okay, the current stayed the same, and the amount of light coming out of it stayed the same, and the second one's actually more or less, oh, I have to change my resistance up to 10 to match it, so it's equivalent with the same current going through both. But notice what happened to the current going through the battery. Is it doubled, so it's now the addition of the two individual currents going through either path in the circuit. And let's see what happens when we plug in a third. Okay, so the third, again, is equivalent to the first two, so nothing changes there. But the battery, again, the current has increased. Now, since nothing's the same, the current and the resistance at each light bulb stayed identical. That means the voltage at each light bulb is actually still identical. Okay, and that's because of our conservation of energy. We'll talk more about this in a second, but the conservation of energy, we can treat each of these paths almost separately. So when an electron comes from the source and it hits this junction, okay, it starts to travel through here. Now the voltage drop, it has a potential difference across the battery of 9 volts, which means if it travels through here and back to the battery, due to the conservation of energy, it has to use those 9 volts. Okay, if it travels through the second one and back to the battery, then that one would also have to use those 9 volts. So each branch in a parallel circuit has the same voltage, which is why we can design a house like this and allow all of our plugs carry the same voltage amount. The current, however, starts to increase with the more things that are plugged in, the current at the source. So if we plug even more in, or for example, if we change the resistance, let's see what happens. I'm going to disconnect one. Let's see what happens if we change the resistance on this one. So we increase the resistance. We see that it doesn't affect the other bulb at all, but it does affect the current at the source, and it will affect, of course, Not the voltage. The voltage will still remain the same, but it'll affect the current here in this branch as well as the current at the source. Okay, so we'll go back down to 10 and hook up this one again. So let's see what happens when we keep plugging things into this. So I've created another circuit over here. And so parallel circuit with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 resistors. So the first 9 are plugged in. Okay, each resistor is 10 ohms like the light bulb. So they're all plugged in. You can see the current at the battery is quite fast. And then as we move out, the ones across all the resistors are the same. And the wire slows down as some of the current goes through each resistor. It progressively gets slower and slower until the last one. Let's see what happens when we plug in one more. Okay, and we've fried our circuit. So we've caused the current to get so high that we've caused a fire. This is exactly what happens when you start plugging multiple power bars into each other. Okay, you have one is fine. Then you plug more and more. You keep adding things in this parallel circuit until the current at the base of the power bar will get so hot, will get so fast, it produces so much energy that it can actually cause a fire to occur due to the heat. So that's why that concept is very important in parallel circuits. As useful as they are, they can be dangerous if used incorrectly. Okay, so let's go back and look at a few of our equations here for parallels. So because the charge has to be conserved, we have our conservation of charge. The total current must be the sum of the individual currents. So here we have IT is equal to I1 plus I2 plus I3, or however many different branches we have in our circuit. Okay, now the voltage, as we saw a minute ago, the total voltage, remains the same across each of the loads. So total voltage is equal to the voltage across load 1, which is equal to 2, which is equal to 3. And that's the great thing about parallel circuits. Now combining these two together, let's take our current equation again. IT equals I1 plus I2 plus I3. And we apply Ohm's law to this. So by substituting Ohm's law, so we're going to use I equals V over R in this case. Okay, we can substitute this and we get V over RT is equal to V over R1 plus V over R2 plus V over R3. Dividing out the V's, we're left with an equation 1 over R1 equals 1 over R2, or sorry, 1 over RT, equals 1 over R1 plus 1 over R2 plus 1 over R3. So this is the equation for our resistance. So again, for parallel circuits, we have our current, voltage, and resistance equations for circuits in parallel. Okay, so let's look at how this resistance, it's a little bit strange, this resistance equation, but let's see what happens. So let's say we have 3 resistors that are 30, all placed in parallel. Okay, so that gives us 1 over our total resistance is equal to 1 over 30 plus 1 over 30 plus 1 over 30, okay, which gives us 3 over 30 or 1 over 10. So now we have this equation. I'm just going to shorten it up over here. We have 1 over RT is equal to 1 over 10. Okay, we invert both sides. We get RT is equal to 10 ohms. So the total resistance in a parallel circuit will actually be less than the resistance on each individual path. The reason for that, if you look at our circuit over to the right here again, okay, the idea, imagine this again as cars driving along a road. Okay, they're moving fine here, and let's say these are roadblocks. So if we only have, so let's just break this for a moment and break this one. Okay, so here we have a resistance of 10 in our circuit. Okay, and we see it's flowing fairly slowly. We put a resistor. This is like a roadblock on the road. So what we do is open up a detour. Okay, we give another path for the cars to go through because we're getting jammed up. Okay, so now they're going faster. Now some are still taking the detour. Some are taking still the resistance path, some are taking this new path that we opened, so it's split between both. What this does is it makes it easier overall for the cars to flow through, or what we're really talking about is electricity. Add a third path, same thing. We opened up a third possibility for everything to flow, so we can get things moving faster here at the base by adding together more. So as a result, what this does is drop the total resistance by adding more optional paths for the current to flow. Let's have a look at an example. Okay, so find the total current leaving the battery in the following parallel circuit. Okay, so the first thing we'll do here is we will calculate, so let's label our resistors first. We'll just call this 1, 2, 3, and we'll calculate our total resistance. So we have 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Okay, and we get that is equal to, so 1 over RT, 1 over 12 plus 1 over 25 plus 1 over 18. So to make this a little simpler, I will change it to a decimal. So if we add those together, we get 0.179. And now what we have to do is invert both sides here. So we get RT is equal to 1 over 0.179, or that our total resistance in our circuit is equal to 5.6 ohms. Lastly, we're asked to find our total current, so that's our resistance. Our total current, we can just use Ohm's law. IT is equal to VT over RT. Since we're looking for the total, we have to use the total voltage and the total resistance. And we get that the total current is equal to 24, which is our voltage from our battery, over 5.6, which gives us a current of 4.3 amps. And the last example here is to calculate the current in each branch. So we have our total current. Now what's the current along each branch in this system? Okay, so if we want to know the current in branch 1, we have to use the voltage in branch 1 along with the resistance in branch 1. The voltage we know is the same everywhere, so 24 over our resistance is 12, and we get a current of 2.0 amps. Okay, follow the same thing for the second two, so I2, and we end up with approximately 1 with some rounding, and I3 is 1.3. And if you add each of these together, you'll find that the I total, which again is I1 plus I2 plus I3, gives us what we calculated in the previous question as 4.3 amps. Okay, so now that we've gone through some series circuits in the last video, some parallel circuits in this one, the next thing, we'll look at a few complex circuits in the next video that will combine series and parallel circuits together into one.